Hello students, I am Dr. Tanmay Vishwas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is about the reaction of butadiene. It's a very interesting molecule. So we will discuss mainly today about the non-pericyclic reactions of butadiene. So you can see this is the structure of butadiene and this is the orbital representation. But before going to the main topic, one MCQ for you. I request everyone, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words of explanation if possible. Now, don't worry, at the end of this discussion, you'll have the right answer. Now, today's discussion will cover few points like reactivity of butadiene, bromine addition, HBr addition, hydrogen addition, Birch reduction, polymerization, etc. So, first go to the basic property or reactivity of butadiene from MO or molecular orbital concept. So whenever we say butadiene, you can say this is actually the butadiene, or more specifically if I say it is 1,3 butadiene. Now in this case these two double bonds or pi bonds are in conjugation. So you may think that okay sir, this way they are bonded. Now even this part they can also conjugate. So there are lots of canonical forms possible. For example, if you look at here, that this double bond can come here and it can open. So what it will result? So here you can see actually this canonical form. So negative charge is here, positive charge is here. Or you can say differently that sir, this bond will go here, it will be here. So negative charge is here, positive charge is. So what message I want to give? That if you look at this butadiene like CH2 double bond CH, single bond CH, again CH2. This double bond is not a completely purely double bond character. If you look at this is a single bond, it's not a single bond character. It has partial double bond character and it has partial single bond character. So you can see here in this two canonical form there is a double bond. So it makes the molecule very unique. If you want to learn little deeper, so you can look at here, means why butadiene is more reactive than isolated alkene. So this is your energy axis, and if you look at these are the pi bond. Actually I say this is the pi of what? The individual, this pi bond. Okay, so this is, and this part is actually the pi star. And in case of butadiene, what happened? These pi bonds or pi orbitals will overlap or conjugate farther. Okay, so what it will result? So when two orbital undergoes conjugation, it produces one low energy orbital like this pi 1. So you may consider that okay, these are pi 1, pi 2, pi 3, pi 4. These are MO, pi and pi star. It's a further combination. So these two orbitals, so this is, you may say sir, it is maximum stable. Why? Because it is the lowest energy. Next is this one. Now even the pi star orbitals can undergo overlap between themselves. It produces this pi star 3, pi star 4 like that. And these actually, if you look at their shapes, it looks like this. What do I mean here? But here is one. I'm not talking about this region. So what do I mean? I'm not talking this. I'm talking the perpendicular version. Here is one nodal plane. If you look at pi star 3, there are two nodal planes, because if you look at the color, there is a change in symmetry. If you look at here, there are three nodal planes like that. Okay, so now there are few points. What is HOMO? HOMO means highest occupied molecular orbital. Means you may say it's a electron filled orbital. What is this? This is LUMO. LUMO means lowest unoccupied molecular orbital. So it is electron deficient. Now why they are important? Suppose you are doing some reaction, means you are reacting butadiene with some electron deficient molecule. So butadiene will act as the electron donor. So which molecular orbital will participate for this reaction? This one, HOMO. Or if you are reacting some molecule which are electron rich, then butadiene is going to accept electron density. Where it will accept electron density? In LUMO. Why here? Why in chi star 3? Why not chi star 4? Remember, electron prefers to stay in the lower energy orbital. The more the low energy orbital electron will stay, more stability it will feel. Means if electrons stay in this pi 3, it has lesser energy, means more stability. Now if you look at in HOMO case, means remember, higher the energy of HOMO, reactivity is more. Lower the energy of LUMO, reactivity is also more, because you are giving electron to someone. If your electron is already having sufficient energy, this donation is far better. So this is actually the conceptual clarity of butadiene. And what is its different compared to isolated alkene? Look at, this is the pi of isolated alkene. So you may say, okay, sir, isolated alkene is comparatively poor electron donor. Why? Because this is the HOMO for isolated alkene, HOMO, and this is the LUMO for isolated alkene. So LUMO energy higher, so cannot accept electron density so much efficiently. HOMO energy is lower, so cannot donate electron density so efficiently. I do not mean that they do not react in that way. They react, but I am saying efficiently or less efficiently from that perspective. Okay, so if you think overall this part in a very easy manner, so you may say, sir, these four orbitals are in overlap, this above lobes and below lobes, and this makes butadiene very unique molecule. Okay, so let's go to its reactivity, like addition of symmetrical reagent bromine. Why I'm saying it's a symmetrical? Because bromine, if you look at both part, is same, so that's why I'm talking it's a symmetrical reagent. Okay, now student, I have already uploaded a dedicated lecture like bromination of alkene. It's this thing, beach bromonium ion. If you have any doubt, you may visit here. I am giving a very brief understanding. Now we know bromine undergoes addition across a double bond, or more specifically if I say pi bond. The pi bond breaks and two new sigma bond forms. So that is the driving force for this reaction. But if you look at in case of this 1,3-butadiene, there are two choices. The addition of bromine could be across this 1,2 or across 1,4. Now, which reaction will take place? It depends on the reaction condition. Means if you take low temperature like 15 degrees centigrade, minus 15 degrees centigrade, it produces major product 1,2 addition. I mean this one. This is 1, this is 2. And 1,4 addition also possible, but that is actually comparatively less. So you may say, sir, this is minor, this is major. Now if you change the reaction condition, means if you increase the temperature from minus 15 to plus 60 degrees centigrade, what happens? So in that case, the 1,2 product, look at here, 10%, so it became minor product, whereas the 1,4 product is 90%, so it is the major product. Okay, so if you can look at the temperature decides that which product will be the major product. Remember, if a reaction follows lower temperature pathway, the product we called as kinetically controlled product, and if the reaction is taking place high temperature, and whatever we get, that's called thermodynamic control product. And actually you may say thermodynamic control product is more stable product. Okay, so kinetically 1,2 addition favored, whereas thermodynamically 1,4 addition favored. Now your question may be, sir, how the reaction takes place or mechanism? Look at here. In low temperature, means actually that time the reactivity dominates. Means if you look at bromine, they are halogen group 17 element, they are electron deficient. They need one more electron to attain nearest noble gas electron configuration. So what will happen? This double bond will attack. By the way, I've already discussed a dedicated lecture regarding this attack, bridge bromonium ion formation. Please visit for further learning. So this double bond attacks here. Remember, this polarity developed in bromine molecule. So this is delta positive. So you may say, sir, these bromine center act as a weak electrophile or mild electrophile. So pi bond attacks here. What it produces? It produces this double bond CH plus here CH2 Br plus Br minus. Now this bromine has three lone pairs of electrons. So one of them lone pair will give, and it will produce this three-member ring cationic species called bridge bromonium ion. This bromine is acting as a bridge between these two carbon atoms. That's why it's called bridge bromonium ion. Next, what can happen? You may say, sir, this bromine can directly attack here, or you may say, sir, it attacks here. Both cases will end up the same product, so it doesn't matter. So it will end up 1,2-dibromo product. But remember, student, that this kinetic control product produced in room temperature or low temperature, means here minus 15 degree. Now this, if you give higher temperature, what can happen? These bond can broken very easily. Directly reaction can follow this track, or the kinetic control product may produce, which undergo further reaction to produce thermodynamic control product. What do I mean? In this bridge bromonium, and if the bromine attacks here, it comes here, it opens. So it will again produce this 1,4-dibromo. Or you may say, sir, some amount is converted to this 1,2-dibromo. What can happen? This bond can be broken pretty easily. Why? Because after this breakage, it will produce a allyl cation, which is resonance stabilized. What do I mean? this pi bond can participate in resonance. So this is Br, this is the positive charge. So this is, now again the next Br minus can attack this positive charge. So you will end up the same product. Or you may think, sir, that under this condition, again what can happen? This bromine lone pair can attack within the intramolecular reaction, and it can produce this bridge bromonium ion, and this bromine can attack here. It will go there, and ultimately this bond will be broken. So ultimate is 1,4-dibromo, but it is high temperature, 60 degrees centigrade. That's why it is called thermodynamic control product, or TCP, and the firster one, initial one, is called KCP, or kinetic control product. So this is the mechanism. So I believe you have understood this. Now let's go to the next point, that is addition of unsymmetrical reagent like HBr. If you look at HBr, it is unsymmetrical because across this sigma bond the two reagents are different. Not only that, polarity is already present here, means this hydrogen is delta positive, bromine is delta negative. So you may say, okay sir, this is the electrophilic center. Yes, you are already have it. Now what happened here? So if you take HBr, means I'm talking this, the delta positive hydrogen get attacked by this pi bond, and this Br leaves. So first protonation here, now produce this one. By the way, if you look at, this is a secondary and allylic. So secondary means 2 plus I effect, one is here, another here, and allyl means these bond, means if I draw it here, CH plus CH3, so it can participate in resonance, so it can come here. So you may say like that, positive charge is here. So it's a resonance stabilized, means the carbocation or positive charge is delocalized, means stabilized. Now what can happen? You may say, sir, this bromine minus can attack here and produce this one option. Now this is at low temperature, or you may say this is kinetically controlled product, KCP. Fine. Now if you give high temperature, what can happen? This KCP will be produced. Now next time this KCP may broken down. How? These bond can break. And what it can result? It can result this cation, carbocation. Again, this carbocation can undergo resonance to produce this one. Exactly this one is drawn here, student. Now what can happen? This bromine will attack there. Okay, so it produces, now if you look at here, hydrogen here, bromine here, so it is 1,4 addition. If you look at the firster one here, this is the hydrogen and this is the bromine, so this one was 1,2 addition. Here also the 1,2 addition is the kinetically controlled product, whereas 1,4 addition product is TCP, or thermodynamic control product, obviously at high temperature. It's a very unique concept. Okay, now let's go to the next point. This is actually the addition of butadiene with HBr under radical condition. By the way, student, you have studied anti-Markovnikov addition. Similar like, but I will not say the word Markovnikov here, it's not, but similar type of condition, means HBr and peroxide. Remember, these peroxides are not very stable molecule. Why? Because this adjacent oxygen lone pair have repulsion which destabilizes them, means alpha effect. So if you give any kind of energy either in the form of heat or radiation, which we represent by H nu, they undergo homolytic cleavage and they produce radical. Okay, radical oxygen 7 electron radical is not a very stable species, because oxygen is an electronegative atom. Actually second most electronegative atom prefers to have octet field. It is 7 electron, not stable. So what it does, it reacts with the HBr this way. Student, this is a half arrow or fish hook arrow, movement of single electron. So it produces the Br radical. So upon reaction of HBr, then this peroxide, it produces the bromine radical. And this bromine radical, by the way, it is also a 7 electron species. So you can say, sir, this is your electrophile. Electron deficient, and these double bond act as the nucleophile or electron rich species, so it attacks. What it result? It produces secondary radical. By the way, why not primary? Because not in conjugation, means not allylic, as well as plus I effect less. Same logic is applicable for here also. Why I am getting this one, not the other one? Same logic. Primary, so less number of plus I effect, and second thing, it is not allylic, so not resonance stabilized. So it will be produced. Now it can undergo resonance. You may think like that, sir, it can come here, it can open, so it and this will come. So there is a double bond here. This is, by the way, this is primary radical, this is secondary radical. Okay, this secondary radical is comparatively more stable. Like it can react with HBr and it can produce this 1,2 product, means this is the addition, and it is your KCP or kinetic control product. And why, you may say, sir, it should be stable? No, it is less stable. Why? Because it is a less substituted. And if you look at the 141 is here, the this reacts with again HBr and regenerate the bromine radical, so it produces 1,4 addition product. It's regenerated, so it is more stable because it's more substituted. Look at across the double bond, one side CH3, another side is CH2Br, so it's a more substituted, more stable. So that's why I guess previous case also you may have this doubt why this is TCP or more stable, because it is more substituted, it is less substituted. Clear now? So this is more substituted double bond and this is TCP or thermodynamic control product or more stable product. So this is the addition reaction. Now next is actually Birch reduction. Student, I guess you have studied Birch reduction previously. There is a sodium liquid ammonia reduction, benzene to this 1,4 hydrogen addition product, unconjugated diene. I guess you have studied them. By the way, if you have not studied it, I have already uploaded dedicated lecture on Birch reduction on benzene. Not only that, a dedicated reaction on butadiene you may visit for further learning. I'll give a very brief. So what this sodium liquid ammonia does? Sodium dissolve in liquid ammonia and releases solvate electron. And remember, this solvate electron is actually the reducing agent. And where the electron is accepted? Student, here, LUMO, the electron is accepted here. Why it accepted efficiently? Because its energy level of electron can be taken very easily. Comparatively to this, it's lower, LUMO. So that's why compared to this place, electron could be accepted in this pi star 3 more efficiently because of comparatively lesser energy than this one. Now, okay, so it reduces. By the way, I'm not going mechanism, you may visit that video, I shall provide the link. Now it produces 40% trans product minor, cis product major. Yes, student, you may feel surprised, sir, why the major product is cis? Actually there is an orbital interaction. I'll provide the video, you'll visit there, I'm not going to discuss it here. So this is another reaction. Now you may ask one question, sir, why the reaction do not proceed further, means these to this, why it stops in the alkene phase? Because previously there is a diene, means 2 alkene, 2 double bond, 1 double bond reduced. After that, why don't? Now if you look at the electron acceptance, now in case of diene, electron accepted here, LUMO, this is my lower energy. But if you look at alkene case, that time the LUMO is this one, so it is comparatively higher in energy, so it cannot accept the electron more efficiently. So that's why reaction does not proceed further and stops at alkene stage. Okay. Now next one is actually hydrogenation. Now it's a very common thing. Whenever you have pi bond, carbon-carbon double bond, in presence of excess hydrogen and catalyst like palladium or platinum or nickel, they can act as catalyst. These hydrogen get added across the pi bond and produces sigma bonds. Means actually you may say 1,3-butadiene to butane saturated analog. And in this case, if you ask me, technically 2 equivalent of hydrogen needed. Why? Because there are 2 pi bond. Each of the pi bond consumes 1 equivalent hydrogen gas in presence of catalysts like palladium, platinum or nickel. Now these are the normal reaction we have started. Next we will discuss about the polymerization of butadiene, okay, or its related molecules, means butadiene derivative, to produce further. Now what is the main concept regarding the polymerization of butadiene? If you look at, whenever you do polymerization of this butadiene molecule, what it produces? So actually if you look at, it has 2 pi bond, 1 and 2, it reacts and ultimately what it produces? This is the original unit. No, not here, here. So one carbon number, I'm talking 1 2 3 4, 1 2 3 4, this. Now if you look at that, 1 pi bond remains, another pi bond is broken down and both sides 2 new sigma bonds are produced. So overall what happens? Carbon-carbon pi bond is broken down and produces carbon-carbon sigma bond. Remember, sigma bond is stronger or more stable than pi bond. Why? Because pi bond is made by parallel or sidewise overlap, which is not very stronger overlap or stable overlap, or extent of overlap is less, so weaker bond. And if you look at sigma bond, this is made by head on or end to end overlap. Okay, in this case it's a sp3 overlap, not pp. So it's a stronger because this electron density is exactly in between the two nuclei, so strongly attracted by both these nucleus. Whereas in case of pi bond, the electron density is just above and below the plane connecting to the nucleus, so it's a weakly attracted. So in this reaction I am producing a stable bond or stronger bond than the pi bond, so that's why reaction takes place. That's the driving force for this polymerization reaction. And this polymerization could be achieved by chemical method, thermal method, photochemical method, or free radical pathway, depending whatever condition you are employing for this reaction. Now let's go for the some examples like related to butadiene polymerization. Now first one, simple polymerization, linear and cross polymerization. So as I told, the same, using the same logic, these two butadiene molecule reacting together means you may think like that, sir, one butadiene, another butadiene. What it will happen? These two end will be connected through a sigma bond. This side and this side, one new pi bond will be broken. Again, this side one sigma bond, this side. So this side will not be reacting. Okay, whatever I mean that this is one, if you follow radical pathway, one radical, these will be again, this is again one radical. In this way it will proceed. Okay, and so it will go on and ultimately it will be. Now sometime what happened, this two double bond not directly participate, one butadiene two double bonds, another butadiene one double bond, such that's why one double bond is left unreacted, and these unreacted double bonds or this bond could be utilized further for cross polymerization, and this helps to tune the properties of polymer, okay, like vulcanization, etc. Now so this is the polymer. Now here if you look at this side, this across this double bond, this group and this group, they are trans, opposite. Okay, it's a trans polymerization. If you look at here, this part and this part, they are cis. So cis trans both are possible. Now next one is actually styrene butadiene rubber, SBR. Student, I recall this is your MCQ. Okay. Now this is styrene. So by the way, you may say, sir, in benzene also there are alternating pi bond. Why don't they react, or do they react under any condition? Answer is no. Why? Because these three pi bonds, that's why they have given a circle, because they are delocalized. Delocalized means they are resonance stabilized, so they will not participate in this chemical reaction, because if they participate in this chemical reaction, their stability will be compromised, so they will not participate. What will happen? This double bond, it is not in the part of aromatic system, it can participate in this polymerization process. So what will happen? This pi bond will go and new pi bond will form in between as it is. Student, I am not going to explain this thing every time, so you should understand this, I believe. So this is styrene butadiene rubber, or SBR short form. Okay, so okay, next nitrile rubber. By the way, if you look at this is acrylonitrile. Okay, it results BUNA-N rubber. So similar, like recall that their case is a previously pH, right now it is CN. This is the thing, everything remaining thing are same. Okay, so it's used in seal industry. Next, isobutylene isoprene rubber. What happened? Look at this, is a different kinds of alkene, both substitution, and here it's not a pure butadiene, it is 2-methyl butadiene, means 2-methyl derivative. So chemically, concept wise, look at both are same, there are 2-methyl and this is here. Okay, so what it result? It result this butadiene, a butyl rubber. Similar. Now next one is neoprene. Now here these butadiene undergo polymerization in presence of K2S2O8. What is K2S2O8? Is double. This is actually persulfate. Okay, so double bond, this is O minus, This is O minus, counter cation is potassium. By the way, recall just sometime before I have told something about the why peroxides are more reactive and they break down and produce radical. Similar, if you look at this region, it's a peroxide. These two oxygen means two adjacent oxygen lone pair faces repulsion. So under reaction condition they break down homolytically and produces two radical. What do I mean? So if I draw, it will be S double bond O, this is O radical, this is O minus K plus. And these initiates the reaction, means it's a free radical polymerization, and here K2S2O8 is the radical producing reagent. Okay, now here as another difference, it's not a pure butadiene, so there is a chloro derivative. Okay, so this results the neoprene. Next, now it is actually the reference from where I have taken these examples. If you want, you may go through. Now what is the conclusion for today's discussion? Remember, butadiene is both stable and reactive. Yes, student, it's a very interesting concept because you may visit the first part of this lecture. Resonance of butadiene means resonance means delocalization. Delocalization means stabilization. That's why I can say butadiene is a stable molecule. Now, if you look at the HOMO energy of butadiene is higher. So from that perspective, means reaction with electrophile, it is more reactive. Again, if you look at LUMO energy is lower compared to simple alkene. So like Birch reduction case, so that perspective also it is more reactive. So it's a very unique combination. Generally we say stable molecules are less reactive, but here the opposite. Stable molecule is also could be more reactive. I have already uploaded a dedicated lecture in this context. You may visit for further learning. Okay, I shall provide the link in the description box and in the I button. Now due to conjugation with 2 pi bonds, this is we get. And so as I told, it's highly reactive for electrophile due to high level LUMO. It can accept electron density easily due to lower energy level of LUMO. By the way, this is HOMO. I guess I pronounced LUMO. High energy level of HOMO, low energy level of LUMO. Now, like ethylene, other alkene means ethylene or other alkene, butadiene can undergo polymerization. Similar way I have explained, and the produced polymer case that pi bond is broken and sigma bond is produced, and in this process there is one carbon-carbon pi bond still remain, and that could be used for further polymerization, cross-linking, vulcanization, like reaction with sulfur such that sulfur forms a bond across the pi bond, so the strength, mechanical strength increases of the polymer. So these are the point we have learned from today's video. Now let's go to our MCQ. What is the structure of the final polymer? So structure, as I told, it's a butadiene, this is styrene, so it will be SBr. So this is the final product. Okay, so this is the overall reaction, student. Thanks for watching. See you in my next video, and if you're watching from YouTube, please subscribe this channel, like, comment and share, and if you look at from Facebook, please like the page, share among your friends. See you in my next video. Bye-bye.